In this video, we will submit a job type for calculation, or in other simple words, we will run a calculation and we will also see what are the components of a Gaussian input file. So if you have drawn the structure of the molecule that you have in your hand, you can go for calculation stage now. I can do quickly with the structure of methane. I draw the structure of methane here, and now I can go for calculation, setting up a calculation. I can go to the tab of calculate and then Gaussian calculation setup. The same thing can be done simply by keys here, Control plus G. If you press Control plus G, you will get the Gaussian calculation setup. A new window pops up here. And you can see in this new window, there are different parameters for setup. You can set the job type. What is the job type you want to select? It can be like energy, optimization, frequency, opt plus frequency. So when you talk about energy, it simply calculates the energy for the structure you have drawn. It does not undergo optimization. I mean, the optimization process will not take place. Only the energy will be calculated for the structure that you have drawn. But when you select optimization, all geometric parameters will be optimized to the equilibrium geometry. And when you have selected frequency, it will calculate the vibrational spectrum. When you select opt plus frequency, it means you are combining optimization plus frequency analysis. You can also select IRC, scan, stability, or NMR, but those are not the commands for the beginners. The very beginners are mostly interested in simply optimization and energy. Let's say we want to optimize this structure of methane. We can select optimization here, and in method, you can see the option for ground state or excited state. If you select ground state, you will have ground state, but if you are interested in excited state calculation, then you can select one of these like ZINDO, CIS, or SAC-CI, or time-dependent SCF. But since we are interested in ground state optimization, we select the ground state. So these are the different methods, like you can use classical mechanics, you can use semi-empirical, you can select Hartree-Fock, DFT, MP2, or any other one. And even if your method is not listed here, you can customize it. What are these methods? We'll see during this lecture series. But right now, for the sake of simplicity, I suggest that you select Hartree-Fock. And then it says spin. You can take restricted, unrestricted, or restricted open. Again, not to confuse you at this early stage, keep the things as simple as possible. We select ground state, we select the method of Hartree-Fock, and we take it to the default spin. Normally for organic molecules, when we don't have like any radicals or other open shell system, we simply select the default spin. So then we have basis set. We keep the basis set as 3 to 1G for the sake of simplicity. We can also select like STO3G or higher basis set. But since this is a demonstration, I can select 3 to 1G. In the next tab, you can put your job title. Let's say if I select methane input file or methane optimization. Then in the next tab, it is called link 0, because here you can select how much memory you want to allocate to this calculation, how many processor you want to select, whether you want to save the checkpoint file or not, you want to save read-write file. So let's say we keep the things to their default value. In their default value, the checkpoint file is saved, okay? And the default value is processor is generally 1, and the memory is about 8 megawords. But you can change if you want to change to, let's say, 10 megawords or 50 megawords. You might be wondering that why the memory is given in megawords. Gaussian takes the memory in megawords, and 1 megaword is equal to 8 megabytes. So you can calculate yourself. If you are going to select, like, let's say 100 megawords, it means you're going to assign 800 megabytes of the memory, which is less than 1 GB. Most of the computers nowadays, even laptops, they have RAM around 8 or 16 GB. So selecting even like 100 megawords is not a big deal. But the default here is 8 megawords. And let's say if I select it to 50 megawords, I will show you where does it pop up in the input file. So let's say I select the processor to 4. And then we have some general other tabs here, which I'm not going to explore at this moment. So far, I have done job type, method, title, and link 0 commands. Once we are done with this, I can ask the software to submit the file. And when it goes for submission, it asks me to save it. And once I save it, in my computer, it takes me by default to downloads. But in your case, you need to be really careful because sometimes new people, when they are saving the file, they don't care or they don't know where the file is being saved. And at the end, they are just struggling to find where the file was saved. So let's say I'm going to save it in my downloads, and I select methane optimization. I save it. And now you can see a new window pops up here, which says Gaussian, and it's going to do optimization here. You can see something quick going on because the molecule is so simple. And now it is done. Once it is done, it says, do you want to close the Gaussian window? And normally we say yes. And if it is yes, a new window pops up here, and it tells you that these two files are generated here, optimization.chk or optimization.log. Some informations are kept in checkpoint file and some informations are in log file. If you want to read the information in the form of text, then it is better to see log file. But sometimes to see graphics like HOMO-LOMO orbitals, you are better suggested to open the checkpoint file. Let's say if I open the log file, and here is the structure which is optimized. Now this is the structure that I gave to the software, and this is the structure that is coming out of the software after optimization. And probably the geometric parameters are not changed much because the molecule is quite simple, but we can have a look. Let's say we look at the bond angles or bond length. In the input file, the bond length was 1.07. And the structure that was optimized, if we look at the bond length, it is 1.0829. It means the bond length has increased. Similarly, if you look at the bond angle in the input file was 109.471, and in the output file, it is 109.4712, almost like identical. So one thing to learn here is that the optimized structure is not exactly identical to your input file, even for this smallest molecule, which is methane. So let's close this and look at the input file. Input file was saved originally in the download folder. We go to downloads and look at the files there. There are 3 files: methane optimization.ggf, methane optimization.log, and methane optimization.chk. ggf is the file that you created as an input file. Log is the log file or the output file, and checkpoint file is also the output file. These 2 files are generated after calculation, and this one is given as the input file for optimization. If you open up the optimization.ggf file, make sure that you want to open it in Notepad. In my computer, the settings are by default in such a way that if I click on this one, it will be opened up in Notepad. But in case in your computer, it is not opening up in Notepad, you can right-click and open with the software of your interest, which is Notepad. You can do open with, and then you can open with Notepad. So now if I open this methane optimization.ggf, I can see this is the input file looking like. On the top 3 line here, it can be 3 or it can be 4 depending on how many link 0 commands have you selected. I selected nproc shared is equal to 4. It means I set the software to use 4 processor for calculation. N is the number, proc is for processor, and shared mean they are working in a shared memory, right? So it tells the software to use 4 processor, and then it says percent memory is equal to 50 megawords. It means this is the memory allocated for Gaussian calculation. And then there is a root for checkpoint file, which is C, users, HP, downloads, and then methane optimization.chk, which is the name. So these 3 lines are called link 0 commands because they are opening up with %, and in the Gauss view, we selected them from the link 0 command. So these 3 are the link 0 commands. After link 0 command, you have the root line, which starts with a hash sign. You can see here, link 0 commands are starting with %, and the root line is starting with the hash sign. And in root line, we said we need to do optimization at Hartree-Fock with 321G basis set. And this geometrical connectivity is telling the software that the Cartesian coordinates are given, but at the end, their connectivity is also given. So these are the Cartesian coordinates, and this is the connectivity. I will show you what is the connectivity meaning here. After the root line, we have a blank line, then title. We said the title is methane optimization. After title, we have again a blank line. And after the blank line, we have charge and multiplicity. And then we have Cartesian coordinates of the structure. Our structure is methane here. So these are the Cartesian coordinates of methane. Cartesian coordinates are shown by like X, Y, and Z values. So the first line shows the position of carbon in X, Y, and Z axis, then position of hydrogen, another hydrogen, and further on. So then we have a blank line. This blank line indicates that the input file in terms of Cartesian coordinate is completed. And below that, we have connectivity. And if you try to read this connectivity, it says that atom 1 bonded to atom 2 with a bond 1.0. It means you have 1.0 bond between 1 and 2. So it means atom 1 and atom 2 are bonded with a single bond. Again, atom 1 is bonded to atom 3, and the bond between them is 1.0. It means again 1 and 3 atom, 1 is carbon and 3 is this hydrogen, they are bonded through a single bond. And then again 1 and 4 are also bonded. What is the bond between them? It is 1.0. And finally, the atom 1 is also bonded to atom 5, and the bond between them is 1.0. So it means what we know from the connectivity here that atom 1 is bonded to atom 2, 3, 4, and 5. And between all those atoms, the bond is 1.0, 1.0, and 1.0. Now, in this line, we have specified the connectivity of 1 and 2, 1 and 3, 1 and 4, and 1 and 5. So when you describe atom 2, 3, and 4, 2, 3, 4, and 5, you don't describe any connectivity in front of it because their connectivity is already described here. And at the end, you again have a blank line. So that is all about your input file. Just a quick overview, you have link 0 commands where you describe the memory, number of processor, checkpoint file, read-write file. Then we have root line, starting with a hash sign where you describe what type of calculation is to be performed and which basis set and method. You have blank line, title card, blank line, charge multiplicity, Cartesian coordinates, blank line, then connectivity, and again a blank line, and that's it. So once you know the component of the components of the Gaussian input file, you can play around with them and modify them according to your own choice. We will see those in a later video.